Predictive Pathways, Modeling and Simulating the Future of Active Mode Traffic. This research vision is behavioral modeling and predictive simulation for future active mode traffic systems, considering the requirements of safety, efficiency, well-being, and sustainability. Most new challenges focus on developing a sustainable future for people and the planet, as outlined by the United Nations. Walking and cycling are key solutions. Promoting active modes aligns with the social development goals, aiming to enhance sustainability, create healthy cities, and reduce carbon emissions. This research vision is built on key building blocks: behavioral insights, advanced modeling, and empirical validation, with a focus on movement dynamics at the operational level. This scope can extend to tactical and strategic levels as well. Here, we have a classic control loop in traditional traffic engineering for decision support, progressing from data and modeling to decision-making. Next, we will explore how traditional traffic engineering applies to active mode research, new research challenges in this field, and how this research vision addresses these challenges. Traditional active modes, pedestrians and bicycles, typically use pedestrian pathways and bicycle lanes. Shared micromobility has rapidly emerged in recent years. The primary focus is on movement and behavior of all active mode users, including pedestrians, cyclists, and micromobility riders, especially in shared spaces where they coexist and interact. To achieve this, we first need data covering various transportation modes. We primarily use open-access mobility platforms and self-collected local data to capture user dynamics at local level. Self-collected data include surveys, interviews, and fieldwork. These animations highlight experiments designed to investigate cycling movements and to study micromobility interactions at the operational level. The goal of these experiments is to understand, model, and manage active mode flows in urban environments. Also, data from public authorities at the global level provides context for active mode infrastructures. For example, GPS data from the Talking Bikes initiative at the national level offers individual cycling traces across spatial and temporal dimensions. Similarly, vlog data at the city level helps analyze the active mode traffic environment. All these data sources contribute to understanding active mode behaviors. For example, we can analyze active mode user behavior and estimate traffic states using predictive models. In this case, by integrating AI techniques with traditional traffic engineering, we can estimate bicycle delays at intersections using national cyclist trajectory data. Behavioral analysis helps generate conceptual insights. For instance, we can use the collected data to derive bicycle headway distributions to calculate saturation flow and bicycle capacity at signalized intersections. Also, to develop conceptual models to describe cyclist queuing behavior, translating this into mathematical models to replicate operational decisions at both mental and physical levels. In summary, behavioral insights and conceptual models are vital inputs for developing simulation models. Here, we show an ideal development cycle for simulation models, starting with conceptual ideas or behavioral findings, which are then transformed into mathematical models and implemented using numerical approaches for simulation applications. Key challenges to closing this cycle include comprehensive behavioral understanding of complex active mode interactions within active mode infrastructures, advanced and efficient numerical solutions to enhance simulation accuracy, validated and effective simulation environments for real-world applicability. We have successfully modeled aspects of active mode behavior within simulation frameworks. For instance, this showcase replicates pedestrian and cyclist behavior in shared spaces using a microscopic simulation environment. We can also apply this to macroscopic simulation. These animations demonstrate how the simulation tool reproduces self-organization phenomena in crowds, such as shockwaves in pedestrian flows, lateral density diffusion, and lane formation. These simulation tools support decision-making in different ways, such as analyzing active mode operations to optimize facility design and daily operations, identifying bottlenecks and evaluating capacity and safety in the design phase, enhancing pedestrian systems at transportation hubs, aiding in timetable planning and optimal placement of information provision systems, facilitating traffic management and infrastructure design for improved efficiency. Again, the research framework consists of key components: data collection and empirical validation, traffic engineering, and decision support. By integrating digital twins and AI with traditional traffic engineering, we can develop adaptive, real-time active mode management systems. While walking and cycling have been well studied, gaps remain in understanding new and emerging modes. The rapid rise of micromobility, including e-scooters, e-bikes, e-mopeds, skateboards, and segways, brings new challenges. We aim to understand how users of these new active modes behave, interact, and impact the environment. Only by addressing these questions can we ensure their safe and sustainable integration into urban spaces. There are still lots of challenges ahead of us, and still lots of unknowns. To list a few, there are limited empirical data and insufficient behavioral insights for new and emerging active modes. This leads to changing safety dynamics with no comprehensive strategies to address risks for new user groups. There is a lack of advanced simulation tools, as existing models lack adaptability and efficient numerical solutions. There is no stable framework for integrating microscopic and macroscopic simulation models. There is absence of ready-to-use strategies for managing and integrating diverse active mode traffic systems. And we see limited integration of advanced technologies, such as digital twins, AI, into traditional traffic engineering. Also, there exists insufficient focus on safety, sustainability, and user well-being in active mode traffic system design and management. Do you find this interesting? Want to collaborate? Feel free to reach out.